Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why sometimes you feel like you are in control of your thoughts and actions, and other times it feels like your brain has a mind of its own? Well, this new research dives deep into how we monitor and control our own thinking. Think about it. We're not just reacting to the world. We're constantly checking in with ourselves, seeing if our plans are working and tweaking things as we go. This all falls under the umbrella of what scientists call Meta-cognition and Meta-Control. It is like having a boss inside your head, making sure the workers, your brain cells, are doing their job, right? But how exactly does this inner boss work? And what happens when it screws up? This research offers a super cool way to think about this using something called the recursive Markov decision process, or recursive MDP for short. Imagine your brain is like a team. There is the main worker agent who deals directly with the outside world. But this worker agent is only human, right? It makes mistakes. It has limits. So there's another agent, a higher level boss. The meta-agent, this meta-agent watches the worker agent and tells it how to do things better. Metacognition is basically this meta-agent observing its own worker agent, and meta-control is the boss agent telling the worker how to adjust its approach. The paper explains that meta-control is about us inferring and representing our own states and those of our environments. We then decide what actions to take, evaluating their potential usefulness based on past experiences or predicted future success. Then we actually do the action and learn from what happens. The tricky part is initiating, regulating, and executing all those statistical and computational operations that make up control. This leads to a recursive problem, Meta-Control, which stems from our own flaws and limitations. For example, to reduce making mistakes, Meta-Control juggles a high capacity, fast. But Inflexible automated or habitual controller with a deliberate controller that has the opposite characteristics. This isn't just some abstract idea. When Meta-Control goes wrong, it can lead to serious problems. Think about conditions like ADHD, addiction, or schizophrenia. Failures in this self-monitoring and self-adjustment system are thought to play a big role in these disorders. It can also contribute to repetitive negative thinking like rumination and worry. So understanding the system is really important for both our mental health and for engineering better artificial intelligence. Previously, different research traditions looked at these aspects separately. One area is meta-reasoning, which is about wisely using information processing. It is framed by theories like the value of computation, or VOC for short. Basically, it asks how much is it worth it to spend brain power on thinking through a problem versus just making a quick decision. Then there's cognitive control, which is about regulating our actions to achieve our goals, like ignoring distractions. This is looked at through the lens of the expected value of control, or EVC. It's about figuring out the best way to control our behavior, weighing the benefits against the cost of that control. What this paper does is brilliant. It brings these different ideas together under one roof. It proposes a common framework, a shared way of talking about meta-control, showing how these different concepts like VOC are really just different faces of the same coin. It helps us see the underlying assumptions and the computations involved in controlling our own control. So, how does this recursive MDP framework actually work? Imagine a base agent that is responsible for dealing with the external world. This agent has to make decisions like deciding whether to take the bus or the train to the airport. It has its own internal planning algorithm like a step-by-step process. This is the base level process. Now, the meta-agent, let's call it the meta-zero agent, watches this base agent. It doesn't directly interact with the outside world. Instead, it observes how the base agent is working. It figures out meta-states, which are like indicators of how the base agent is performing. For example, the meta-zero agent might look at the base agent's planning process and see how confident it is about choosing the train versus the bus. It also looks at how deep the planning tree is, meaning how many steps ahead the base agent has considered. Using these meta-states, the meta-zero agent then chooses meta-actions. These aren't actions in the outside world, but rather commands to the base agent. For instance, the meta-zero agent might decide to tell the base agent to stop planning and just pick the train, or it might tell it to spend more time planning by expanding the search tree to consider more possibilities. Like what happens if there is a traffic jam? This meta-action of continuing to plan costs something in terms of time and brain energy. And here is where it gets really mind. Bending the system can be recursive. The meta-zero agent can also be watched by another boss, a meta-1 agent, which oversees the meta-zero agent. This can go on, creating a hierarchy of control. The paper highlights metacognition as being like meta-perception. Just like our eyes perceive the external world, our metacognitive system perceives our internal cognitive processes. These meta-states can be generic, meaning they're useful for controlling many different kinds of thinking processes. These include things like how much progress we're making towards a goal, how confident we are in our conclusions, if there is a conflict between ideas, or how quickly we're learning. But there are also specific meta states that are tailored to particular thinking tasks. For example, if the base agent is a specific planning algorithm, the meta agent might monitor very specific aspects of that algorithm's performance. Similarly, meta actions can be generic or specific. Generic meta actions are broad commands like deciding to abandon a task or start searching for more information. Specific meta actions are more fine-tuned adjustments. An example is setting an exploration parameter in a planning algorithm. Think of it like telling your worker agent to either stick to what it knows or to go out and explore new options more boldly. The paper visualizes this spectrum from highly specific meta-controllers for particular algorithms like Monte Carlo tree search or MCTs to very general ones that can oversee a wide range of cognitive processes. Generic meta-controllers are like a general manager who can oversee any department, while specific ones are like a specialist manager for the marketing team. The trade-off is that general meta-controllers are more versatile but less precise. They can apply to many situations but can't fine-tune things as much. Specific meta-controllers, on the other hand, are very precise for a particular task but can't be used elsewhere. They give a detailed example using Monte Carlo tree search, or MCTs. This is a powerful planning algorithm used in AI, like in the game of Go. For MCTs, states could be things like the balance of the search tree or how much confidence has improved from past simulations. The meta actions then might involve adjusting the exploration parameter within MCTs or deciding when to stop planning and make a move. The meta-control system itself can run using different algorithms, just like the base agent. They can be model-free, which are fast and simple but less flexible, or model-based, which are slower and more complex but can adapt better to new information. The EVC framework, which we talked about earlier, fits nicely here. The Meta-0 agent decides on the control signal for the base agent. It tries to get the best outcome for the base task, minus the cost of using that control. Many studies suggest that the brain uses model-free approaches for these meta-control functions. This means it learns through trial and error, adjusting its control strategies based on experience, rather than building a complex internal model. The VOC framework about choosing computations is also explained with this recursive MDP idea. Here, the meta agent decides not just on a control signal, but on which computations the base agent should perform, weighing the expected benefit against the computational cost. A challenge with model-based meta-control is the risk of an infinite loop, where each level of control needs its own meta-controller, leading to turtles all the way down. The paper addresses this by suggesting that higher levels operate on a slower timescale with more compressed information, making the recursion manageable. The researchers also lay out some of the big unanswered questions. Computationally, they ask, why do we even use meta-control? When do its benefits, like learning faster and generalizing better, outweigh the cost of being computationally demanding? How many levels of this control hierarchy can we actually have? And how does meta-control change as we become experts in something? Does it get simpler or compiled into the base process? On the neural side, they wonder, what are the specific brain signals that represent meta-states like confidence or conflict? What are the meta-sensors that allow the brain to perceive its own internal processes? What are the range of possible meta-actions the brain can take, and do higher-level meta-controllers exist? And if so, are they in different brain areas? They suggest that the brain likely uses similar machinery for meta-control as it does for regular control, but with some privileged meta-states and meta-actions. For example, areas like the anterior cingulate cortex are known to be involved in monitoring conflict and errors, which are key meta-states. Prefrontal cortex regions are also implicated in computing confidence. Understanding the underlying base algorithms the brain uses for things like planning will be crucial for figuring out what is generic and what is specific in meta-perception. The brain has to integrate information from the base algorithm, its own behavior, and environmental cues, which is a big challenge. Neuromodulators like dopamine and norepinephrine might be involved in sending some of the broader generic meta-action signals, affecting things like our overall arousal or how vigilant we are. More specific meta-actions like directing attention to certain features likely involve more flexible top-down control from areas like the prefrontal cortex. The existence of higher-level meta-controllers, supervisors of the supervisors, is still a big mystery. Some research hints at hierarchies in the prefrontal cortex, but it's a complex area. From a computational theory standpoint, the research proposes that meta-control allows us to find really good, but not necessarily perfect solutions to complex problems that would otherwise be too hard to solve optimally. It is about resource rationality, making the best use of our limited cognitive resources. A key challenge is that if you have too many recursive levels, the system can become unstable. Imagine trying to teach a whole chain of people simultaneously. It can get chaotic. So, figuring out when meta-control is actually beneficial and how many levels are feasible is important. Another interesting point is the idea of flattening meta-control. This means that as we become experts, the sophisticated meta-control processes might get compiled and integrated into the base-level controller, making it seem like we're just acting automatically. This is how skills become fluid, but it also makes it tricky to study the meta-control part separately. The paper also brings up meta-information seeking and meta-exploration. This is about the meta-agent actively trying to learn more about how the base agent is performing. This could involve self-testing or even comparing ourselves to others to gauge our progress. Similarly, meta-exploration is about the meta agent learning better ways to guide the search or planning process itself. In conclusion, this research provides a powerful unified framework, the recursive MDP, to understand the complex interplay of metacognition and meta-control. It bridges the gap between computational theories and neural implementation, highlighting critical questions about how we monitor and adjust our own thinking. This is really fascinating stuff. It suggests that our ability to manage our own minds isn't just some magical thinking cap we put on. It is a complex computational system with potential for both incredible efficiency and significant breakdowns. Understanding these mechanisms could revolutionize how we treat mental health conditions. And it is going to be incredibly exciting to see what artificial intelligence can do when it masters this kind of self-awareness and self-correction. What do you guys think? How often do you feel like you are consciously directing your own thoughts? Let me know in the comments below. If you enjoyed this dive into the mind, please give this video a thumbs up. Subscribe to RUBIN'S Mind Lab for more science breakdowns and hit that notification bell so you don't miss our next exploration. Thanks for watching, and I'll see you in the next one.